Alright, let's go. Number 10. Metallic hydrogen in Jupiter's core. Deep within Jupiter's interior, approximately 10,000 kilometers beneath the swirling cloud tops, hydrogen undergoes a transformation that defies everything we understand about the lightest element in the universe. Under pressures exceeding 4 million atmospheres and temperatures reaching 10,000 Kelvin, individual hydrogen atoms are crushed so close together that their electrons break free and flow like liquid metal. This is metallic hydrogen, the same element that floats invisibly through Earth's atmosphere, transformed into a shiny conductor rivaling copper. Eugene Wigner and Hillard Huntington predicted this impossible state in 1935, but it remained purely theoretical until NASA's Juno spacecraft arrived at Jupiter in August 2016. By precisely measuring the planet's gravitational field and its powerful magnetic field, 14 times stronger than Earth's, scientists confirmed that metallic hydrogen comprises roughly 80% of Jupiter's mass, forming a shell 40,000 kilometers thick. This vast ocean of metallic hydrogen generates the planet's intense magnetosphere through dynamo action, creating auroras at Jupiter's poles 1,000 times more powerful than Earth's northern lights. In January 2017, researchers Ranga Dias and Isaac Silvera at Harvard's Lyman Laboratory claimed they had created metallic hydrogen at 495 gigapascals using diamond anvil cells. The implications were staggering. If this material could remain metallic at room temperature, a piece the size of a fingernail could fuel a rocket to Mars with specific impulse of 1,700 seconds, nearly 4 times better than the best chemical rockets. But within hours of achieving this breakthrough, the diamond anvil catastrophically failed. The sample vanished, and despite attempts by laboratories worldwide, no one has definitively replicated the result. Jupiter guards its metallic heart jealously, and we remain unable to recreate what nature manufactures in planetary abundance, a metal made of gas forever beyond our reach. Number 9. Quasicrystals from the Khatyrka Meteorite. In 2009, mineralogist Luca Bindi was examining samples in a Florence museum when he discovered something that mathematics had proven impossible. A meteorite fragment collected from Russia's remote Koryak Mountains contained a crystal with 5-fold rotational symmetry, an arrangement forbidden by the fundamental laws governing how atoms can tile three-dimensional space. Classical crystallography, established over centuries, permitted only 2, 3, 4, and 6-fold symmetry. 5-fold symmetry cannot fill space without gaps, yet here it was, staring back from electron diffraction patterns with perfect geometric precision. The mineral, later named icosahedrite, consists of aluminum, copper, and iron atoms arranged in a pattern that repeats periodically. It has long-range order without true periodicity, like an infinite Penrose tiling extending through 3 dimensions. In 2011, Princeton physicist Paul Steinhardt led an expedition to the Chukotka region, recovering additional samples from the site. Radiometric dating revealed the meteorite was 4.56 billion years old, formed during the violent birth of our solar system when asteroids collided at velocities exceeding 5 kilometers per second. What makes this discovery particularly unsettling is its vindication of decades of ridicule. When Israeli scientist Dan Shechtman first observed quasi-crystalline diffraction patterns in rapidly cooled aluminum manganese alloys in 1982, the scientific community dismissed his findings. Linus Pauling, winner of 2 Nobel Prizes and one of chemistry's most respected figures, publicly declared there are no quasi-crystals, only quasi-scientists. Shechtman faced such fierce opposition that it took 2 years to publish his results. In 2011, he received the Nobel Prize in Chemistry, finally recognized for discovering a new form of matter. The Khatyrka Meteorite proves the universe creates what we believe impossible, forging mathematical anomalies in the chaos of cosmic collisions while we argue about whether they can exist at all. Number 8. Superfluid helium-3 in neutron star crust. On a winter day in 1972, Douglas Osheroff, David Lee, and Robert Richardson at Cornell University cooled helium-3 to 0.0025 degrees, above absolute zero, and watched it transform into something that shouldn't exist. A superfluid with zero viscosity that flows without friction, defying every intuition about how liquids behave. This quantum fluid can flow up the walls of its container, drip through molecular-sized pores, and rotate forever without slowing down. The discovery earned them the 1996 Nobel Prize for revealing that quantum mechanics could manifest at scales visible to the human human eye, but the universe had already been creating this impossible material for billions of years. Not in cryogenic laboratories, but inside neutron stars. Stellar corpses so dense that a teaspoon of their matter weighs as much as Mount Everest. At densities between 100 billion and 100 trillion grams per cubic centimeter, helium-3 and other light elements in the neutron star's inner crust undergo Bose-Einstein condensation, forming superfluids at temperatures of 100 million Kelvin. Anthony Leggett predicted this phenomenon theoretically in 1972, work that earned him the 2003 Nobel Prize. The evidence appears in pulsar glitches. The Vela pulsar, located 1,000 light-years away in the constellation Vela, is one of the most stable clocks in the universe, rotating with microsecond precision. Yet every 3 years on average, it suddenly spins faster, its rotation period decreasing by 1 part per million in seconds. The superfluid interior rotates independently from the solid crust, gradually building up stress along quantum vortices, tornado-like structures in the superfluid. When these vortices suddenly unpin from the crust, they transfer angular momentum in a violent release that makes the entire star convulse. We're watching quantum mechanics operate on cosmic scales, kilometer-sized objects exhibiting behavior normally confined to ultra-cold atoms in laboratory traps. Inside neutron stars, quantum superfluids store and release rotational energy across light-years of space. Their glitches detectable by radio telescopes as the universe's strangest clockwork mechanism stutters and lurches forward. Number 7. Carbyne chains in interstellar clouds. Floating in the vast darkness between stars are chains of carbon atoms bonded in perfectly straight lines, the strongest material known to physics, with tensile strength twice that of graphene and stiffness several times greater than diamond. Theoretical calculations predict Carbyne can withstand forces of 100 million newtons per square meter before breaking, representing the ultimate limit of material strength possible in our universe. Yet for decades, chemists struggled to create even small amounts in laboratories because Carbyne is so violently reactive it destroys itself within milliseconds on Earth, cross-linking into graphite or reacting explosively with oxygen and water. In 2016, astronomer Michael McCarthy and his team at the Harvard-Smithsonian Center for Astrophysics used the Green Bank telescope and ALMA array to detect long carbon chains in the envelope surrounding IRC plus 10216. A dying carbon-rich star 500 light-years away in the constellation Leo. They identified chains up to 13 atoms long, cyano-octtetraene, and other linear molecules with alternating triple bonds that should be impossible to maintain. The column density reached 10 trillion molecules per square centimeter, suggesting that up to 10% of carbon in certain interstellar regions exists in these linear chains. The discovery reveals a cosmic irony. Space naturally manufactures in abundance what represents one of chemistry's greatest synthesis challenges. In the near vacuum between stars, where temperatures hover around 10 to 50 Kelvin and reactive molecules are essentially absent, carbon atoms assemble into configurations that would instantly collapse in Earth's atmosphere. The same year astronomers confirmed Carbyne's prevalence in space, Rice University researchers finally synthesized stable carbine in the laboratory by protecting the chain ends with bulky chemical groups, a technique that mimics how space's isolation preserves these fragile structures. What remains unsettling is the realization that the universe casually produces materials we can barely create, scattering the strongest substance possible through clouds of gas forever beyond our ability to harvest or study directly. Number 6. Strange quark matter. In 1984, physicist Edward Witten proposed something that challenges the most fundamental assumption about matter, that protons and neutrons represent the most stable configuration of quarks. His calculations suggested that at densities exceeding 500 trillion grams per cubic centimeter, conditions found only in the cores of the most massive neutron stars, quarks might break free from their nuclear prisons and form a soup of up, down, and strange quarks existing in a state called quark-gluon plasma. Even more disturbing, Witten's equations indicated this strange quark matter might actually be more stable than ordinary atomic nuclei. If true, this means every atom in the universe exists in a metastable state, like a ball balanced on a hill waiting for the slightest push. A single strangelet, a microscopic droplet of strange quark matter, touching ordinary matter could theoretically trigger a conversion chain reaction. The nucleus converts to strange matter, releases energy that creates more strange quarks, and the process continues, converting everything it touches. In the most extreme scenario, a strangelet could theoretically consume an entire planet, transforming it atom by atom into a dense sphere of quark matter. Since 2000, the relativistic heavy ion collider at Brookhaven and the Large Hadron Collider at CERN have smashed gold and led nuclei together at energies approaching those present microseconds after the Big Bang, creating quark-gluon plasma that exists for 10 to the negative 23 seconds, before condensing back into ordinary particles. Despite thousands of collisions and dedicated searches, no strangelet has ever been detected. Safety reviews in 1999 and 2008 concluded that even if strangelets exist, they pose no danger. If the conversion threshold were low enough to threaten Earth, cosmic rays would have triggered it long ago. Yet observations of neutron stars with masses exceeding 2 solar masses suggest something beyond neutron degeneracy pressure supports them. The equation of state at these extreme densities remains genuinely unknown, and strange quark cores represent one plausible explanation. We may be living in a universe where the most stable form of matter isn't what we're made of, but something far denser and stranger, hidden in stellar corpses scattered across the galaxy. Number 5. Metallic oxygen at ultra-high pressures. For 24 years, scientists attempted to achieve what seemed impossible, transforming oxygen, the gas we breathe, into a metal. In 1998, physicist Mikhail Erametz at the Max Planck Institute claimed success at 96 gigapascals, but other laboratories couldn't replicate his results, and the claim remained disputed. Then in July 2022, Philip Dalladé Simpson and Eugene Gregorians at the University of Edinburgh finally confirmed the transformation in a paper published in Nature. Using diamond anvil cells to compress oxygen to 960,000 times the atmospheric pressure, they watched the pale blue molecular solid transform into a dark red metallic conductor. At these extreme pressures, oxygen molecules are forced so close together that their electron orbitals overlap, creating a delocalized electron C characteristic of metals. The phase transition occurs precisely at 96 gigapascals, where the material's electrical resistance suddenly drops and it begins reflecting light like polished metal. X-ray diffraction revealed the atoms had reorganized into a monoclinic crystal structure, with electrical conductivity reaching 100,000 Siemens per meter, comparable to semiconductors and increasing with pressure. This exotic state isn't confined to laboratories. Deep within the ice giants Uranus and Neptune, at depths exceeding 20,000 kilometers, pressures reach 200 to 600 gigapascals. At these depths, the ices, water, methane, and ammonia, dissociate under extreme conditions, and oxygen separates to form metallic layers. This discovery finally explains one of planetary science's persistent mysteries: why Uranus and Neptune possess bizarre, tilted magnetic fields unlike any other planets in the solar system. Instead of simple dipole fields like Earth's, these ice giants have complex multipolar magnetic fields tilted up to 60 degrees from their rotation axes and offset from their centers. The metallic oxygen layers generate electrical currents that create these chaotic magnetic fields. Their complex geometry, shaped by convection patterns in conducting fluids, we can barely model. The element essential for human life exists inside these distant worlds in a form so alien that bringing a sample to Earth's surface would cause it to explosively decompress back into breathable gas within microseconds. Number 4. Time crystals in extreme gravitational fields. In 2012, Nobel laureate Frank Wilczek proposed something that seemed to violate the laws of thermodynamics, a structure that repeats in time rather than space, oscillating forever in its ground state, without consuming energy. He called them time crystals, and most physicists initially believed they were impossible. In 2015, several papers claimed to prove time crystals couldn't exist in equilibrium systems, seemingly ending the concept. But in 2016, Norman Yao at UC Berkeley reformulated them as discrete time crystals that could exist in periodically driven systems, and within months, 2 independent teams created them in laboratories. In October 2016, Chris Monroe's group at the University of Maryland used 10 ytterbium ions cooled to microkelvin temperatures, while Mikhail Lukin's Harvard team employed nitrogen vacancy centers in diamond at room temperature. Both systems exhibited the defining characteristic of time crystals. They oscillated at half the frequency of the driving force, like a swing that goes back and forth only once for every 2 pushes. These weren't ordinary oscillations, but manifestations of broken time translation symmetry, where the system's ground state spontaneously chooses a preferred rhythm that persists indefinitely. Now, theoretical physicists propose that time crystals might form naturally in the universe's most extreme environments, near black holes, where space-time curves so severely that space and time become fundamentally interchangeable. The intense tidal forces and frame-dragging effects from rotating black holes could organize infalling matter into states that oscillate through time itself, creating quantum structures that exist at the intersection of general relativity and quantum mechanics. This might explain quasi-periodic oscillations, mysterious X-ray brightness variations observed in black hole systems like GRS 1915+105 and Cygnus X1. These oscillations occur with frequencies between 0.1 and 1000 Hz, remaining stable to better than 1% precision over decades of observation. Conventional models attribute them to orbital motion or disk instabilities, but what if we're detecting the signature of time crystalline matter forming in accretion disks? If confirmed, it would mean black holes don't just warp space, they crystallize time itself, creating perpetual quantum oscillations powered by the curvature of reality. Number 3. Superfluid dark matter. In 1933, astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and discovered they were moving far too fast. The cluster should have torn itself apart unless it contained 400 times more mass than visible matter could account for. He called it missing mass, and for 4 decades, most astronomers ignored him. Then in the 1970s, Vera Rubin measured rotation curves of spiral galaxies and confirmed that stars at the edges orbit at the same speed as those near the center, flatly contradicting Newtonian gravity. Something invisible, dark matter, comprises 27% of the universe's mass energy, holding galaxies together through gravity alone. In 2015, physicist Justin Khoury at the University of Pennsylvania proposed something disturbing. Dark matter might not be individual particles drifting through space, but a superfluid, a quantum condensate, extending hundreds of thousands of light years that behaves as a single coherent quantum state. In the cold, dense environments of galactic halos, dark matter particles undergo Bose-Einstein condensation, forming a quantum fluid with zero viscosity that flows without friction. This superfluid naturally produces an emergent force that mimics modified Newtonian dynamics at low accelerations, while maintaining standard physics at larger scales. The hypothesis gained startling support in March 2018, when Peter von Dockum's team, using the Dragonfly telephoto array, discovered galaxy NGC 1052DF2, located 65 million light-years away. This galaxy contains normal stars in globular clusters, but appears to have virtually no dark matter. Its velocity dispersion measured only 10 kilometers per second, where conventional models predict 200. If dark matter consisted of individual particles, this would be impossible, but superfluids can be scooped out during high-speed collisions, like water splashing from a bowl. The bullet cluster collision, long cited as proof that dark matter is particulate rather than modified gravity, actually supports the superfluid model. The collision speed of 4,500 kilometers per second far exceeds the superfluid sound speed, allowing the dark matter to pass through without friction, just as observations show. We might be embedded in an invisible ocean of quantum fluid, with every galaxy floating in a coherent quantum state, containing a billion trillion particles acting as one. Number 2. Excitonium in white dwarf cores. For 50 years, physicists searched for a quantum condensate. That theory predicted, but experiments could never confirm. Excitonium, a material formed when electrons bind to electron holes, the absences left behind, when electrons are excited out of their normal positions. These bound pairs, called excitons, typically exist for only trillionths of a second before the electron falls back into the hole and they annihilate. But if excitons can be made cold and dense enough, theory suggested they might condense into a superfluid state, flowing without resistance like liquid helium at absolute zero. In December 2017, 2 independent teams finally confirmed excitonium's existence. Peter Abamonte's group at the University of Illinois used momentum-resolved electron energy loss spectroscopy on titanium diselenide crystals, detecting a characteristic soft plasmon mode at 50 millielectron volts, the smoking gun signature of exciton condensation. Below 190 Kelvin, the material transitions into an excitonic insulator phase, where excitons form a coherent quantum state, but the universe had anticipated this discovery by billions of years. In 2019, the European Space Agency's Gaia spacecraft released data on the cooling sequences of over 100,000 white dwarfs, the Earth-sized stellar remnants left when sun-like stars exhaust their fuel. The data revealed something inexplicable. White dwarfs aren't cooling as smoothly as physics predicts. At temperatures around 15,000 Kelvin, they show a pronounced pileup, spending approximately 8 billion years longer at these temperatures than models allow. The leading explanation: as white dwarfs cool and their carbon-oxygen cores reach critical densities exceeding 1 million grams per cubic centimeter, they undergo excitonium phase transitions. The condensation releases latent heat, approximately 10 to the 46 ergs, equivalent to what our sun produces over millions of years, temporarily halting the cooling process. Some astronomers speculate that excitonium formation might even trigger certain white dwarf super supernova, causing sub-Chandrasekhar mass explosions that standard models cannot explain. Dead stars are crystallizing into quantum states that challenge our understanding of matter, and we only discovered the phenomenon exists because laboratory physicists finally caught up to what stellar corpses have been doing for eons. Number 1. Topological insulators in Magnetar crusts. On December 27, 2004, a blast of gamma rays struck Earth from 50,000 light-years away with such ferocity that it ionized our upper atmosphere, disrupted satellite communications, and saturated every gamma-ray detector in the solar system within milliseconds. The source was SGR 180620, a magnetar in the constellation Sagittarius that released 10 to the 46 ergs of energy in 1/10 of a second, more than our sun will produce in 250,000 years, concentrated into a burst shorter than a heartbeat. The initial spike was followed by a pulsating tail lasting 400 seconds, modulated at the magnetar's rotation period of 7.5 seconds, as the stellar surface rang like a struck bell. Magnetars are neutron stars, with magnetic fields reaching 10 to the 15th Gauss, a quadrillion times stronger than Earth's magnetic field, so intense they warp quantum electrodynamics itself and generate electron-positron pairs spontaneously from vacuum. How can stellar remnants just 10 kilometers across, spinning once every few seconds, maintain such extreme fields and generate catastrophic energy releases without any fuel source? In 2018, physicist Matthew Kaplan proposed an answer that connects quantum topology to cosmic violence. Magnetar crusts might contain topological insulators. These exotic materials, discovered in laboratories in 2007 and recognized with the 2016 Nobel Prize in Physics, possess a remarkable property. They insulate internally, but conduct electricity on their surfaces with zero resistance. Electrons in topological surface states move in one direction only, their paths protected by quantum topology that makes them immune to defects and disorder. In magnetars, at densities 100 trillion times greater than water and magnetic fields strong enough to elongate atoms into needle-like shapes, the nuclear pasta in the inner crust, matter compressed into rod, slab, and tubular geometries with names like spaghetti, lasagna, and bucatini, might undergo topological phase transitions. These transitions would create surface states where electrical currents flow perpetually without dissipation, generating and maintaining the extreme magnetic fields indefinitely. When stress from magnetic field evolution triggers sudden topological rearrangements, stored magnetic energy releases catastrophically, the giant flares that make magnetars the most violent objects in the cosmos. We're witnessing matter in a state where quantum mechanics, nuclear physics, and general relativity converge at their most extreme intersection, creating perpetual quantum currents on stellar surfaces that transform dead stars into cosmic engines powered by topology itself.